This is part 2 of lecture 1.3 of Math 108, Logical Equivalence. In this video, we will present some basic logical equivalences and use these instead of truth tables to derive other logical equivalences. The following result is a list of basic properties of the negation, conjunction, and disjunction operators stated as logical equivalences. You are required to memorize these. Each of these properties can be proved by comparing truth tables. This is left as an exercise. Let P, Q, and R be arbitrary propositions. First, we have the negation of a proposition P is logically equivalent to P. This is the double negation law. The disjunction P or Q is logically equivalent to the disjunction Q or P. And the conjunction P and Q is logically equivalent to the conjunction Q and P. These are the commutative laws. The statement either P or either Q or R is logically equivalent to the statement either P or Q or R. The statement P and both Q and R is logically equivalent to the statement both P and Q and R. These are the associative laws. Each of these propositional forms may be written without grouping symbols. The statement either P or both Q and R is equivalent to the statement either P or Q and either P or R. The statement P and either Q or R is equivalent to either both P and Q or both P and R. These are the distributive laws. Take note that for these propositional forms, the grouping symbols are required. The negation of the disjunction P or Q is the conjunction not P and not Q. The negation of the conjunction P and Q is the disjunction either not P or not Q. These are De Morgan's laws. Each of these equivalences can be proved by showing that the truth tables of each pair of propositional forms are the same. This is left as an exercise. The next result gives some basic properties of the implication and by implication operators stated as logical equivalences. As for the previous theorem, you are required to memorize these properties. Each of these can be proved by comparing truth tables. This is left as an exercise. First, recall that the conditional sentence P implies Q is logically equivalent to its contrapositive not Q implies not P. We showed this using truth tables in an earlier example. Next, recall that by the definition of the implication operator, the conditional sentence P implies Q is true exactly when either P is false or Q is true. Now, the condition that either P is false or Q is true is the same as the condition that either not P is true or Q is true. Therefore, the conditional sentence P implies Q is logically equivalent to the disjunction either not P or Q. Third, the negation of P implies Q is logically equivalent to the conjunction P and not Q. This is because P implies Q. This is because the negation of P implies Q is true if and only if P implies Q is false. This happens exactly when P is true and Q is false. Fourth, recall that by the definition of the by implication operator, the biconditional sentence P if and only if Q is true exactly when both conditional sentences P implies Q and Q implies P are true. Therefore, the biconditional sentence P if and only if Q is logically equivalent to P implies Q and Q implies P. The proof is again left as an exercise. There is a way of showing the two propositional forms are equivalent without having to construct truth tables. This other method uses the following properties of logical equivalence. We state these here without proof. In this theorem, P, Q, and R represent arbitrary propositional forms. First, any propositional form is logically equivalent to itself. Second, if P is logically equivalent to Q, then Q is logically equivalent to P. And third, if P is logically equivalent to Q and Q is logically equivalent to R, then P is logically equivalent to R. As an example, let us consider the propositional forms not both P and Q, P implies not Q, and Q implies not P. We shall show without using truth tables that these three propositional forms are logically equivalent. Instead, we shall use only the basic logical equivalences in the previous theorems, as well as the three properties of logical equivalence in the preceding slides. First, observe that by one of De Morgan's laws, the statement not both P and Q is logically equivalent to the statement either not P or not Q. Recall that P implies Q is logically equivalent to either not P or Q. Thus, by replacing Q with not Q, the disjunction either not P or not Q is logically equivalent to the conditional sentence P implies not Q. This proves that the statement not both P and Q is logically equivalent to the conditional sentence P implies not Q. The conditional sentence P implies not Q is in turn logically equivalent to its contrapositive, which is the conditional sentence the negation of Q implies not P. By the double negation law, the negation of Q is logically equivalent to Q. Therefore, the sentence P implies not Q is logically equivalent to the sentence Q implies not P. This proves that all three propositional forms are logically equivalent. To illustrate, suppose that n is an integer and that P is the sentence n is odd and Q is the sentence n plus 1 is odd. The sentence, it is not the case that both n and n plus 1 are odd, has the propositional form not both P and Q. This is logically equivalent to the sentence either n is not odd or n plus 1 is not odd, which has propositional form not either not P or not Q. This is logically equivalent to the sentence if n is odd, then n plus 1 is not odd, which has propositional form P implies not Q, and to the sentence if n plus 1 is odd, then n is not odd, which has propositional form Q implies not P. These four sentences have different forms but are all logically the same. In this next example, we show that the conditional sentence P implies both Q and R is logically equivalent to the conjunction P implies Q and P implies R. Recall that the conditional P implies Q is logically equivalent to the disjunction either not P or Q. Thus, by replacing Q with the conjunction Q and R, we can write the conditional P implies both Q and R as the disjunction either not P or both Q and R. By the distributive law, this is logically equivalent to either not P or Q and either not P or R. Either not P or Q is equivalent to P implies Q. Either not P or R is equivalent to P implies R. Therefore, the statement P implies both Q and R is logically equivalent to the statement P implies Q and P implies R. To illustrate, suppose that A and B are real numbers and that P is the sentence the product AB is not equal to 0, Q is the sentence the number A is not equal to 0, and R is the sentence the number B is not equal to 0. The sentence, if the product AB is not equal to 0, then A is not equal to 0 and B is not equal to 0. As propositional form, P implies both Q and R. This is logically equivalent to the sentence, If AB is not equal to 0, then A is not equal to 0. And if AB is not equal to 0, then B is not equal to 0, which has propositional form P implies Q and P implies R. Observe that in the first statement, we use a comma before the word then to indicate that the consequent of the conditional is the entire statement A is not equal to 0 and B is not equal to 0. In the second statement, we use a comma before the word and to indicate that the two statements in the conjunction are the sentence if AB is not equal to 0, then A is not equal to 0, and the sentence if AB is not equal to 0, then B is not equal to 0. Thus, again, we have two sentences that have different forms but are logically the same. You have come to the end of lecture 1.3. Before you proceed to lecture 1.4, be sure that you answer the exercises given at the end of these slides. Thank you for your attention.